And so today what we'll do is we'll go through a review and talk a little bit about the midterm that's coming up on Wednesday. And yeah, that'll basically be our activities for today. And so this will be recorded. The review notes that we'll use are the ones that are online. They're no different from the ones that were used last year. And the recording of what we talk about today will also go online. And it's no different. I've already said in my emails, I'll repeat it. No different from last, well, it will be different from last year, but it's the same idea as last year. So I guess the podium lights are on. See a little different, bright whites. Can people see what's up there? Okay. Are the lights the same as they usually are? Seems like it's darker backwards, but lighter forwards. So, for some reason, if this is set differently, so I know. That's right, exact opposite. Maybe you can't see that. So, so that's the plan for today. We probably don't need this, so you know where to get the material from. We'll use this. We have this exactly here. All right. So, all right. So it's not for 3 today, but you can look at the video online. I think there's an extra credit quiz for it. So because of the particular timing of this, so we're a charitable class. So the assignment that you now will be able to do for week 4 will not be due on Thursday, but will be due on Sunday. The extra credit quiz for 4-3, instead of being due 2 periods ahead, as in Wednesday evening, is Friday evening. So do it before Thursday or Thursday, Friday. And the midterms on Wednesday. Also coming up on Wednesday is this 5-week that you should have made contact with your group. There's no penalty for you if you have not made contact with your group for the presentation. But I think as after this Wednesday the 5th week, Shengji will send you an email to open it up for your topics for your presentation. And so that may be the last thing that's on your mind right now, but first come, first served. I guess we already had one email sent in about what one group wants to do, and so it's probably good for Sheng to do that. So he'll just arrange something on Canvas so you can upload your topic. First come, first served, because we won't duplicate topics. So it's 2 topics on one, or 2 groups doing one single topic, basically. Then the second group will have to figure out something else. Okay. So I will send an email. I think I'm going to send an email every Friday to be able to itemize these things, because I don't expect you to, well, some people are not here. I think Shengji counted last time, we have 83 out of 310, so that's fine. So people are taking it online, absolutely no problem. But the stuff that we talked about today will be recorded, is being recorded, as you know, and it will go online. So the test. Same as in last few years. It won't be multiple choice. It never has been for the last few years. Nominally 90 minutes, an hour and a half, but starting at 8 o'clock and going until midnight, until you can, well, maybe even beyond, if you wish. It depends on how willing Shengji and his compatriots are to stay with you. The exam's written. I went through it. Took me an hour and a half to get through it. I bet you some of you are faster than I. And so I think I always say this. I think it's a fair test. I think it's maybe longish, but it allows you to show what you're doing. But that's always my comments, and I'm sure you won't believe me if I say that. Or maybe you do. It's 3 questions. 330 points. The grade is out of 100, or 300 rather, I guess. Equally weighted questions. There is a question on linear and angular rotational accelerations. There is a question on manometry, fluid pressures in liquids and fluids, part of manometry, and fluid pressures on structures. And there is a question on fluid pressures on structures. So those are the three questions. I'll probably put that in the email as well if you didn't get it down. But if you still have a question, or do you want me to repeat something? First question is on rotational and linear accelerations. Basically 4.1, class 4.1. The second one is on manometry, manometers, pressure measurement devices, and also fluid pressures in them, going up and down. And also fluid pressures on structures, centroids of planes and depths to centroids and those kinds of things. And the third one is on pressures on structures also, but a structure that is failing, a gate type question, an overturning dam type question. So, okay. So my hope is for you to show me your best. I mean, that's why I'm telling you this. So it allows you to maybe focus on things, maybe allows you to be less anxious about things. And so that's my motivation for this. And so the review notes are the ones which are here. So my plan, so I'm happy to answer any questions on that. I won't answer questions on what's not on the test because it seems like there's an intrinsic liability there. But you told me this wasn't there. But the other thing I guess you can do is, since these things are recorded over the years, what you could do is you could go back to 2015 and 2014 and 2013 for which you have the exams, and you could check what was said in there, and you could determine whether I'm spinning you a line or not, if you so wish. So I'm sure you're all very adept at taking exams. You've taken many in your career. You don't need my advice on how to do them. In my view, the third question is actually much more straightforward than it looks, and is perhaps easier than the other two. And so you can weigh out things about what you attack first and those kinds of things. So, okay. All right. So my plan is just to kind of go over what we've done for the first 3 weeks and 1 period, right? It includes 1.1 through to 4.1, which is the material that's on it. That's why the website is laid out that way. And of course, you can go through the material that we've gone through at your leisure online. I haven't looked at the YouTube hits for that to see how many people are doing that, but I guess we could, for instance. Let's just take one that I was definitely here for. So, until the first test, we were really talking about first test. 168 views. Well, we have 310 in the class, so some of you are definitely here for it, and some wouldn't have been. Some of you who are here might not have been here for it, which is perfectly fine, of course. So anyway, actually, you can look at the analytics on Google, and you see this big spike before tests, which is fine. That's what they're there for. So people have to use them in whatever way they wish. Right. So my plan is just to go through this. So any questions before we just start rolling? Yes?
Where is the exam?
Oh, sorry, yeah. 100 Thomas. It's in the big auditorium in Thomas. I think it's 100. I'll send that out in the email as well. And so some of you who have a PNG fluid and rock properties, come at 9 o'clock when you're done. And yeah, so it's in 100 Thomas. All in one room. Sometimes we're split between rooms. Protocol, so equation sheet, can have anything on you want. And we're going to ask you to hand your equation sheet in with your script. So I'm curious to see what people have on there. But come prepared to lose your equation sheet, calculator, pencil, etc. Closed book, If people ask questions to clarify things, we usually put them up on a Google Doc, which has been spread between multiple rooms when it's been in multiple rooms, and so that you get the benefit of other people's questions, and so it's hopefully fair. Yes?
Do we get this equation sheet, or is it just whatever we bring with us?
You can make whatever you want. Yeah, okay. There's no warranty involved. This is the stuff in the notes, so you need to make your own. And it can be anything you like, yeah.
In front and back, too.
Yeah, 2 sides. And on the edges if you wish. All right? Yes? Yeah, I've never got into that game. One that probably doesn't have stuff on it, I suppose. We've never enforced that. I guess you shouldn't be using your phone as a calculator. Keep your phones out. Stuff in your backpacks. I guess, I was talking to some of my colleagues at UT, talking about exams now with the concealed carry law and what people might have in their backpack when they put them at the front of class, etc. Whether you're allowed to have them put their backpacks at the front of class. Bizarre stuff, but that doesn't come here. Yes? Sorry?
What time is it?
It is 8 o'clock on Wednesday. What time is it now, or what time is the exam? The exam, 8 o'clock. Well, no, it is also 8 o'clock. On Wednesday, the whatever the date is, coming Wednesday. I guess September 11, 12, 13, 14, 15. It's 21st, Wednesday the 21st, yes.
What day is the conflict of exam?
There is no conflict exam.
I actually had a class.
What class?
Dance.
Dance?
Yeah.
Come and see me afterwards. 100 Thomas. 100 Thomas. Okay. Anything else? All right. Okay. Well, so for those, so you can listen to this. Those coming. 3 questions. Accelerations, linear and rotational. Manometry, fluid pressures acting on structures. Fluid pressures acting on structures that can fail. Components, right? So with that in mind, we'll go through talking about what we've been through in the class. This should all be old school to you now in terms of these things. You know what the difference between mass and weight is. Oops. I'll make this smaller. You know this is weight, which depends on what planet you're on, and mass, which does not. We know the ideal gas law, absolute pressures, absolute temperatures, a coefficient which relates them. We know what compressibilities are, that depends on changes in pressures with volume or changes in pressures that occur with density. Because if you change volume with the same mass, by definition you change density. We know about wave speeds in confined media, as you're hearing me now, as the modulus divided by density, or the celerity wave, which is just a function of the depth of the fluid and the gravitational acceleration. We know about viscosity, the mechanism by which we lose energy in systems, which conforms to Newton's law of viscosity, which relates a shear stress that you apply to a velocity gradient that gets established, and the coefficient that links those is the coefficient of viscosity. And we talked about both vapor pressure and surface tension. So those are kind of our summary slides. In terms of materials, well, I guess we've already said it. If you were to need the gas law, make sure that you use absolute temperatures and pressures, because that's important. Make sure you use the appropriate gas constant for the particular gas in question, or if you use the universal one, it's divided through by the mass, molar mass of the material, which is if it's the universal gas constant. It depends on how we change volumes, whether it's isothermal or isentropic. Isothermal means you allow all the temperature that's generated when you compress it to dissipate, so T is equal to 0, and if that's equal to 0, then the ratio of pressure to density is always constant. If it's insulated and you keep the entropy in it as you do something to the gas, then you have to account for the fact that you deal with this ratio of the specific heat capacities at constant pressure and volume, which is a number, which is usually a little bit more than 1 if you need it. We've talked about stiffnesses or compressibilities of materials. So compressibility as you would use, for instance, in compressibility of gas in a reservoir, is just 1 over the modulus, the bulk modulus. We can get the bulk modulus from this expression that we introduced briefly before, but maybe the one interesting result that comes out of this is that the modulus of a gas is very, very low, and it's actually equal to the pressure at which that gas is. So we know that the modulus of the gas that surrounds us, mainly nitrogen, is equal to 101 kPa, which is atmospheric pressure in this room, but not on the top of Everest, and not otherwise. Okay. We talked about Newton's law of viscosity. Viscosity is just a coefficient that links together some stress that gets applied, where that stress is equal to some force divided by the area over which it is applied. And we relate, we relate that to a velocity gradient. And the velocity gradient comes because we have these stuck conditions, that the fluid is stuck at 0 velocity on this bottom plate and is attached at some finite velocity on the top plate. And so the change in velocity that occurs over some distance is just the change in velocity over the distance over which it occurs. This is the, so if V is the top one here, this is 0, then delta V is just V. And so this is this expression here. And so if we know what this assumed velocity gradient is, how it changes over a small length, and we know what the applied stress is, we could calculate the viscosity. If we knew what the viscosity was, and we knew either one of these terms, we could calculate how much force you have to apply to do it, or what the velocity would be of this plate if it was moving in this fluid. And so that's how we've used that, and you've used that in examples. We deal only with Newtonian fluids, just because this is an introductory course, but real fluids are sometimes nonlinear. They don't have a, if you double the stress that you apply, you double the velocity. That's all that a Newtonian fluid says. And and so we deal only with Newtonian fluids, not drilling muds, which would be thought of as Bingham fluids or thixotropic or ideal plastic fluids. Okay. We've talked about capillary rise or interfacial tension. This is one particular exposition of that, I guess, in that it looks at how high fluid would rise in a capillary. It follows along with force balance that we've used in other things as well. And it draws on a couple of observations which we've only dealt with a bit more belatedly, and that is that we can cut this thing off at the bottom. We can cut this thing off the bottom because we know that if we go to any two connected points that you can get from one to the other one that are on the same elevation, by definition the fluid pressures have to be the same. If the fluid pressures happen to be the same, then we can cut this off at the base. And we know that the fluid pressure acting up here is just atmospheric pressure, which is also the same as the fluid pressure acting down here. And so we can just ignore them if we take fluid pressure to be gauge pressure, which is 0. Can't always do that. Note that point. But in the case where we're looking here, the fluid pressures cancel out because we're taking atmospheric as 0, and that's just, and we're doing everything else in gauge pressures. And so the solution for this is just to cut this off and draw a free body diagram that looks like this, that has this weight of this fluid hanging downwards, has a force T, which is on the circumference of this, pulling upwards or at some angle and doing the balance. And if you do the balance with an angle, you get this. And if this is actually equal to, theta is equal to 0, then actually this is just 1. And so that's a standard result, but you know how to derive that. I think you know how to derive that because one of your questions in your assignments was, well, calculate the fluid pressure in a bubble. And the only difference is you have to take the surface tension on the inside of the bubble and the outside of the bubble. But you've done that. Okay? So that's in first week. We talked then about fluid pressures in fluids and how they vary, either in liquids or in gases. We made the point that this is always absolutely true, locally, at a point, always absolutely true. If the fluid happens to be a liquid and the density, so I guess for a liquid, the density is large and the modulus is large. And so the consequence of a modulus being large is that density doesn't change very much with pressure, I guess. So density is not a function of pressure. Then we can take the density as constant. If we take the density as constant, then we can usually always use this expression here. And this is just a corollary of that you know of fluid pressure with depth. We've drawn this many times. This is dz and this is dp. And by definition, because of this expression, dp is the same as gamma, this is the same as 1, and unit weight. And this is always true in a liquid. We did an example where we allowed the density to change as you go 6 kilometers down in the ocean, and we saw that it changes by 2%. It doesn't change very much. And so we can always get that in a liquid. And you certainly know how to do that. You've done many, many examples with that. So you know that this is true. If we work with a gas, then as we mentioned before, this is still absolutely true. But now with the gas, then density is a function of pressure. And it conforms to this. You're not going to have to derive this kind of equation. You can see from the other tests if you looked at them, hopefully. But we get a standard result. And if that's the case, the standard result tells us that the pressure varies like this. We've drawn, actually it's worthwhile drawing it again, right? So we've often drawn pressure. Say this is the surface of a lake. We know that in our coordinate system, z is vertically upwards. If we look at fluid pressures, then this would be P atmospheric, which is on the surface of the sea, what we've experienced now. This, like before, is 1 over unit weight. This is positive z in our coordinate system. This is negative z. And we know that the distinction, I guess, is that as we go up above here, then this is not linear anymore. Still at any point though, however, this will always be 1 unit height, and this will always be unit weight of air, and this would be the unit weight of water. They're different from each other, and we've talked about this. And so this demarcation, if you like, this line here, would just be atmospheric pressure. And so this illustrates quite nicely, I think, that when we go down in a liquid, it varies linearly, it changes quite rapidly. When we go up within a gas, then it changes non-linearly according to this law, but this gradient is so inconsequential compared to this gradient, is why in the manometry equations, if you go up and down in a liquid 2 meters, in a gas 2 meters, we don't care. It doesn't make any difference. And so we usually take the pressure within the manometer in a gas traditionally to be zero density, to vary. So on the interface of a liquid to any place above that, in a gas as you go above it, it's the same pressure. We've done that. The other laws that we haven't proved, but we've hopefully taken on trust, is that the pressures act all in the same direction at a point, and they're the same magnitude, or in all directions. And I guess the point that we've already made is that if you want to go if you can get from A to B without going through a solid surface, then by definition, if they're on the same elevation, they have to be at the same pressure. And so I don't know if we talked about this in class, but in this case, if you had an example that had a cap on the top of it, some unknown fluid pressure here, you would know that atmospheric pressure acts here, and you could always work your way from atmospheric to this point. You could work from your way to this point, and then you could work your way from this to this point, and you could figure out what this pressure is. And that's basically the principle of manometry that we use. Okay. Okay. Manometry, again, I mean, I think it's just exactly that routine. And I suppose the rules of manometry, we have maybe 4 of them, right? If you go up in a fluid, if you go up, you subtract pressures. If you go down in the fluid, pressure increases, so you add. So that's the first. If it's in a gas, we set the density basically equal to 0. And the repercussion of that, or the result of that, is that as you climb up and down a gas, you take it as constant pressure. And if a gas is at vapor pressure, then you take it as that pressure. If a gas has been in an evacuated place and you've pulled it like in a barometer, then it has to be the minimum pressure in a gas. P gas min is vapor pressure. I don't think you need that. But so I think the easiest way to do these are to go from a place where you, I guess maybe do it in the opposite direction from this, right? This here we started at A. So pressure A minus 10 meters times this unit weight. Same pressure across here. Plus 5 plus 5 plus 2. 5 plus 5 plus 2. That gets us here. We can go across here to this point here. And then minus 2 minus 5, which is 7, with mercury. Gives you this atmospheric pressure. I suppose you could have probably more easily worked from here, because then you end up with P atmospheric, and then you end up with it being equal to PA, and so you have that. But you can just switch the signs on this and get the solution. But that's basically this. All of these, I guess if this was, for instance, a gas, if fluid, the white fluid here was not water, then I guess you could just get rid of these as zeros, and you'd have a different solution. So you have to be maybe a bit careful with that. So manometry. So you move up and down within the fluid. So you just need those rules. If you go up, you subtract. If you go down, you add. If you go horizontally within the fluid, it has to be the same pressure at those elevations. If you go up in a gas, then you don't bother about the unit weight. So those are the manometer rules. Pressures on structures. What do I want to do this or not? Maybe. I'll make a point. The point isn't very well made in these figures, I don't think.
That manometer problem, how can you assume that the atmospheric pressure is zero?
You could assume it's, well, yeah, so you would calculate from this, if you assume that this pressure here is pressure gauge is equal to 0, then all the pressures that you'd calculate would be relative to pressure gauge. If you assumed that the pressure was an absolute pressure, which is equal to 101 kPa, then the value that PA you'd get would be absolute pressure. That's all. So that's an important question, actually, for the manometer question that you end up doing. For instance, if you're working with resultants. Yeah, so remember that. Remember atmospheric and gauge pressures. Keep that in your mind. So hydrostatic forces acting on structures. I guess there are three things to remember, and I'm going to write them down here. One is we can calculate the resultant. And the resultant force, I think, is always given by an area, a unit weight, and the depth of the centroid. We can now calculate the location where it acts, and we've often called that y sub r. And y sub r is equal to, if I can remember right, 1 over x sub c yc plus, no, not plus, times area plus yc. And we can always get this by taking moments about any point we want, absolutely any, because we're just looking for rotational equilibrium, moments anywhere. And the third is that if we want to look at failure, we need to take moments about the failure point, if you like. Failure mode. So to get the forces that act on the structures and where they act, as in number 2, you can take moments, always, about any point that you want. But if you want to figure out whether a gate is going to open with a particular hydrostatic force or resultant acting on it, you have to take moments about the hinge point of that gate. Otherwise it won't tell you whether it will open. So I think that's maybe a subtle point, but it's maybe an important one. So I think these are 3 important rules for the third question, which is kind of, I said already, is a failure question. This is too complicated. Fluid pressures act always at the center of pressure, but their magnitudes are always given by the resultant, which we've already written, which is the area of the plate times the unit weight of the fluid multiplied by the depth of the centroid. The centroid of the surface on which it acts. It's a depth, and so it's a vertical component. So the depth of the centroid is always a vertical depth from the surface to that point. If the plate happens to be only, doesn't intersect the surface, then the area of the plate is going to be only the area that you see in section here. The location of the centroid is going to be in the centroid of that plate, and it would be exactly at this point here. Always a depth. And I say that because if you look at the location of the resultant is always this value, which we've called y, which is in the plane of this inclined plate. Not the vertical distance from the surface, but the inclined length. And so the magnitude of the force is always given by this expression, always. But the location where it acts is always given by what we've called y sub r, which is shown as hr here. Happens to be a height here, but it would also be a y direction. And y in this case is always in the plane on which it acts. So that's an important consideration. Oops, didn't mean to do that. And I don't know whether this diagram figures it. You don't need to know this. But if the plate is inclined, as this is trying to show, then you can always get the location of it, the slope distance from the surface. It's always about the surface. This has to be the water surface here. And it's always this first moment of area about the x-axis. So it's taken about this axis here. That's what this means. It's the first moment of area of the centroid relative to the x-axis. That's what this means. If you need these equations, you'll be given them. It's something like this, I believe. Check if it's right. I'm pretty sure that's right. But for a structure, this of course is a centroid in the middle of it. And so if it's inclined, then both the y coordinate of the centroid and its y coordinate of this where the pressure acts are both in the plane of the plate, the inclined plate. And so you have to remember that. So this really is y. If the plate's vertical, obviously it's the same as depth. But if it's not, then it isn't. And what this says is that the center where the pressure acts, the center of pressure, is always at the centroid plus a small amount. It could be at the centroid if this is 0, but it always has to be below it. And so if you calculate a depth where it's acting and it's above it, then that probably isn't right. Okay? Calculate the resultant force, it's a depth. Calculate where it acts, it's in the plane of the thing. This is it here. This is what we just wrote. I guess the A's and B's are switched in what I just drew. This always has to be, the depth downwards. This is the y direction. And so all I did when I did this was I switched these, I think, right? So if you need these, you'll be given them. You might want to put them on your sheet and understand what they are, but if you need them, you'll be given them. Forces on curved surfaces. You can always identify a free body. We did this in class. You can go back to it. I'll try and mention the important points. You want to calculate what the forces are acting on half of this. Make a free body and look at the forces that have to act. If you isolate this, then you know the forces have to be this triangular distribution here, for which there's a resultant. The pressure acting on the top has to be 0 if you take atmospheric as gauge pressure. And if that's the case, we know we could calculate F1 as being equal to unit weight times the area times the depth of the centroid. The depth of the centroid would be 1.5 feet in this case. And the area would be 3 feet by 1 inch of the page. Where does it act? Well, you know that for this structure you could use the y sub r thing, but you know that this one acts 2/3 of the way down. 2/3 of the total length. So 2 feet down in this case. So you know both the magnitude of this, of the resultant, and you can calculate where it acts. You know that since there's only one force acting horizontally, it has to be the same as this. So that's all this is here. If you know what's acting vertically, you can calculate the weight of this, which is just the area of a quarter of a circle multiplied by a meter into the page. And you can multiply that by unit weight, and that would give you the value of W, which you can get. And you know that has to be equal to FV. And you know that for any structure, the center of gravity of that structure is its centroid. That's by definition what it is. So you know exactly where that acts. So if you wanted to, you could take moments of F1, which you know where it acts and how big it is, and this location around any point, and you'd end up with 0 moment for these. Or you could take moments about FH and FV. You know that the resultant force here, going into much more detail than I wanted to, is equal to square root of FV squared plus FH squared. So you know the magnitude of this force. And so if you wanted to, you could take moments of this force relative to these two other forces. And you'd find out that actually, because all the fluid pressures act against this surface, it physically has to act through this point here. The point we made about a tainter gate being able to be flimsy because of that. You can do exactly the same for the case where you have a supernatant fluid on it. Again, this is exactly the same problem as before, and it differs only in the fact that we have a vertical force acting downwards here. And so all that would be, you could think of it in a couple of different ways. You could think of this as a pressure distribution, which is equal to unit weight times the depth, HA. And so then the resultant force, F1, is going to be equal to the pressure times the area of that plate. Or you could also think about this as being equal to the unit weight times the area of the plate times H sub C. The centroid of this plate here is going to be this, and therefore HA is HC. So you can do it a couple of different ways. And so the only difference between this one and the previous example is that now we have a new force which comes into this. If you want to calculate what the resultant is, you could definitely get the resultant by just taking the sums FH squared plus FV squared, just as before. But now the vertical component just has an extra part due to this extra surcharge on it. If you know the magnitude of this, you can also take moments about any point. The easiest place to take moments about would be this, and you'd find out that the lever arm for FR would be 0. Actually, it wouldn't be in this case. It wouldn't be 0 in this case. It would act differently through that. So you could take moment arms for F2, W, and F1 relative to FR, and you could find the moment of action. And you could use trigonometry to figure out from the relative lengths of these exactly the direction of action. Okay. Spending too much time doing this. We did this in class, so I won't go through it. The key is to realize that this point here is at the same elevation as this point here, and therefore has to have the same pressure, and therefore the pressure distribution on this part of the cylinder has to look like this. If you take a free body. It may be a bit, I hope I'm not confusing people, but there are 3 ways we can do forces on structures, and we've talked about each of them in class. So if you look at this example, it's just a gate with fluid behind it. We could calculate the resultant force on this in 3 different ways. We could do it by just taking pressure triangles, which is the easiest one, and looking at the magnitude of the resultant force and its location being 2/3 down it, and we get the result for both FR and YR. We could do it by taking, again, the same equation for the resultant force, but using the first moment formula to calculate where it acts on an inclined plane, which is the second way we talked about. Or we could do it using a free body diagram to take the area underneath the gate and to resolve everything like we just did in this particular case here. They should all give exactly the same results. And this one page hopefully demonstrates to you exactly that they give the same result. And so if you're unclear about what's going on, then at least look through here and verify for yourself that you get exactly the same results for this. Well, it becomes a complicated example, but it's a relatively straightforward example. The second question has a buoyancy, a trivial buoyancy question in it, which I didn't mention. Buoyant forces are equal to the volume of fluid displaced. And so we talked about concepts of calculating what the buoyant force is. It's just equal to the volume of fluid that's displaced multiplied by the unit weight of the fluid that is displaced. Again, it all relies on free body diagrams. We can do a free body diagram for this being pulled down by some tension. There's a buoyant force which is equal to the volume of this multiplied by the unit weight of fluid displaced, and maybe it has a weight as well. And so if we resolve these, if we know what the buoyant force is, we know what the weight of the thing is, then we can calculate the tension. If we know what the force is, for instance, which is the tension, which is out of balance, if it is out of balance and we let go, then we can calculate an acceleration from that, if we wanted to. And you'll see in other questions we've done that. We said that one of them is, the first one is about both linear and rotational acceleration. So a couple of results. One is that if we accelerate a fluid linearly, we know that it will slop up against the back of a glass. We can calculate the slope of that surface, and it will be given by this equation at the bottom, which you wouldn't have to derive, but let's just write it up here. dz dy is equal to ay over g plus az minus. And that says a couple of different things. It says that the slope of this, if you accelerate it horizontally, is governed by this expression. If there's no net upwards acceleration, az, then this would be 0, and the gradient of this would just be the ratio of those two terms, ay over gravity. If there is a vertical component, then the slope would change slightly, and so you can calculate that from that. That's a standard result that you can use, and you can look at what we talked about in class. If you look at the pressure distribution in this, then the pressure distribution is always given by pressure acting all directions is equal to, I guess, the depth, which I'll call h, multiplied by g yes, it's a plus. Actually, this term here, which says that if there's no vertical acceleration, it's just your normal triangular distribution that you have, and you can now calculate how pressure changes with depth. If it's accelerating upwards, just like feeling your legs in an elevator, the pressure force in your legs as you accelerate upwards is larger. And so you'd expect this pressure distribution in this fluid everywhere from the free surface to be increasing like this. If it's doing the opposite, it'll be less. And so this is a key result. If you're accelerating downwards at just free falling, then the pressure distribution would be unit weight. I guess this is it here. This is that same expression. Did I put a unit weight in there? Density. Yes. So exactly this point here and this expression here, if you just take dz as a finite number. And finally, rotational accelerations. It's going at constant velocity, but we can calculate, for instance, what this free surface looks like from this. The slope of the free surface will be this. And so if we know at what radius we are, we know what the gravitational acceleration on the planet is, and we know what this is in radians per second. And what do we have? V theta is equal to R omega, I think. Sleepy? Then we can calculate what this gradient is. If we wanted to integrate this expression, then we get one of our standard results. I'll leave that there, which is this, which is how z changes as we go outwardly from a location. It has a constant in it, so it makes it a bit more complicated for us because we have to anchor it to a particular value. But nonetheless, if we can evaluate what z is at a known place, at a known radius and a known rotational speed, then we can calculate what c is, and then we can use that to calculate what z is at some other location at a different radius. And we did an example in class for that. And if you look at the fluid pressures within a fluid, then I suppose if you look at this surface that's being twisted around this center line, then if you looked at the pressure distribution that you had from this going downwards, if this is H rather than Z, then the pressure would just be equal to, bless you, pressure is equal to what we just said before, which is equal to unit weight, density times gravity plus acceleration in the z direction multiplied by whatever the depth is. So in other words, if this thing is spinning around and it's just sitting here on this planet, then there is no extra acceleration upwards, and so it's just the unit weight with depth that we see. If it is getting accelerated, if it's going up in an elevator for some bizarre reason, I don't know why it would be, but then there's a vertical acceleration that we'd have to deal with. And it adds to gravity going upwards, and it subtracts from gravity going down. I think that's it.